Okay, let's talk about some strategies that can be used for methods of green design. First one is design for manufacture. Now, design for manufacture, we're going to break it up into a few different parts, but in a nutshell, it basically means to design a product to make it easy as possible to be assembled. This reduces costs for a company because if they can make it easy for their workers to assemble, they're going to end up having to have less people working on doing the process to assemble it, and then the actual manufacturing process will also be simplified. Basically, the biggest way to do this is to use standard parts and replaceable designs, or replaceable parts and standard designs. That's usually the method that most companies are going to choose. Lots of products are designed to be assembled in several different pieces. Very few things are actually one single part. Very few products, that is, are just one solid piece of material. It happens a few times, but typically you're going to have a series of different components, and the more of it can be automated, usually the less expensive, the more reliable, and the less waste is going to be created by manufacturing. Now, remember, the light background is going to be on the tests for 2016, so just be aware of that. Now, this is just kind of a reiteration. Design for manufacture is in pretty much every product line when it comes down to it, but the implementation is different depending on what manufacturing processes are needed to use. Focus is not just on the components, but also labor, quality control and assurance, distribution, all of that kind of gets into it. Regarding international mindedness, you want to link this to the way new technologies are being used and how they can impact regions all around the world. Like 3D printing, for example, is kind of a big one, and this is the first time that I've seen IB actually mention 3D printing. But this is a neat process because it's all about the machine that does the manufacturing. The person who's running the 3D printer doesn't need to have any real skill set. They can just download a plan, run it on their printer, and end up with a specific product or design. You can design your own, or you can download them. If you're interested, go take a look at the website thingiverse.com. It's run by the people who make the popular MakerBot series of 3D printers. They have thousands upon thousands of crowdsourced 3D printing parts that can be made for all different purposes. Everything from artwork to technical things to mundane things. Like you can 3D print replacement pegs that go into like drawers to add new shelves. If like one of them broke, you can 3D print one. Someone's actually bothered to take the measurements and make one of those. So there's a lot that's out there. Why should design for manufacture play a big role in the design brief? For manufacture, a lot of times is the biggest part of a design brief, because when you think about it, ease of assembly, the efficient use of materials, minimizing the amount of waste, minimizing the different types of materials that are needed, and the use of available tools, machines are a lot of times those are the biggest parts of getting a product to market and actually manufacturing it. Now, design for manufacture is split into design for materials, design for process, and design for assembly. Now let's look at each of these. Design for materials primarily revolves around designing a product so that it uses less or less expensive or more abundant resources. Design for process is designing a product so that the processing of the materials requires less energy, less resources, and also there's less steps that are involved. Designing for assembly is designing a product so that it's simple and inexpensive to assemble. Remember, fewer parts means that a product can be assembled quickly and for less cost. Also, if you remember the SME video that you should have watched, fewer parts means you can make something, you can make an individual part so complicated that the machining equipment required to tool that part is extremely expensive. So there is a bit of a balance here too. Discuss three strategies that designers could employ for design for manufacture. Now, some of the strategies that are listed are minimizing number of components, using standard components, designing components that are multifunctional for multi-use, designing parts for ease of fabrication, minimizing handling, and using standard sub-assemblies. Now, using standard components and standard sub-assemblies is commonly referred to as using standard parts or commercial off-the-shelf parts. You'll see this in industry under the acronym COTS. That just stands for commercial off-the-shelf. Stuff that you can buy in any store anywhere. How and when can designers impact the outcome of design for manufacture? Designers can modify the environmental impact of production and pay attention primarily by using life cycle assessments that has been described in previous slideshows. This aids design for manufacture because designers can actually design a part so that it has standard replaceable parts. For example, cell phones that have batteries that can be replaced. That way, when a battery starts holding less and less of a charge, as it frequently does, the end user is able to order a new battery and easily replace that on their own. If they use a standard battery size, it's easy to find something like that online, buy it, and then replace your battery. And now instead of having a phone that lasts 3 hours on a charge, it'll actually last a whole day. You can also use standard memory cards, micro SD cards, or whatever else, or standard size screws that can be easily found and replaced. Define reuse, repair, recondition, and recycle. You've probably heard of these things before. Reusing is to use something over again. Repair is simply to fix it. Recondition, and that should be underlined, is basically to fix and modify something and use it for a different purpose. Recycling revolves around disassembling, separating, and breaking down materials to form completely different products. How do they help? Basically, the big takeaway from this is that all of these things optimize resource utilization, or that is, they allow for resources to be used more efficiently and reduce the number of resources that need to be used. Take a look at how these strategies can be applied to the design of product, including packaging. Well, let's take a look at a few things specifically. Here's a neat example. Disposable cameras, and here's a picture of a disposable camera right here, disassembled. Disposable cameras are actually surprisingly green. You think about disposable cameras, and you may or may not even ever used one with how common cameras on cell phones are these days. But with a disposable camera, you take pictures with it, and when it's done, then you can't use it anymore. But in order to get the pictures out of it, you have to take it somewhere, and they will disassemble the camera, take the film out, develop the film, and give you the pictures. Now, with what's left over, that chassis gets sent back to the manufacturer. They will replace the battery, recondition it, and reload it with film, and then resell it. So disposable cameras are actually surprisingly green when you think about it. There's not a whole lot of waste. You don't throw them away when they're done. They're not really disposable. You're going to get several lives out of these things, but you just don't see that because they get sent back to the manufacturer, who will then recondition and resell them. Vacuum cleaners. They've been designing vacuum cleaners more and more to use either reusable or no filtration systems, or filtration systems that can be easily cleaned and removed. Car tires are neat because you can actually, if a car tire gets damaged, you can retread them and reuse them. So even when it's completely flat, they can be reconditioned and reused and still be used on and on and on. There's three material groups that can be easily and economically recycled. The big ones are three specific things. You can recycle a lot of things, but thermoplastics, metals, and glass are all easily recycled. because all of these can be broken down with just heat. Thermoplastics are plastics that will remelt. We will get into that in topic 4. Metals, we'll also get into topic 4, can easily be melted as long as you sort them into the proper types and know how the alloys work. And then glass is one of the easiest. Glass and metals are probably one of the two of the easiest things to recycle. And there is actually some value in metals. A lot of people recycle metals, and actually you can get money for taking them to the scrapyard, which actually has become a problem around the Cleveland area. All of these, it's easy to melt them down. Paper can be recycled. Paper products can be recycled, but that process is a lot more energy intensive, and it can also require a lot of use of specific chemicals to clean and bleach the papers. You don't need any of that for recycling thermoplastics, metals, or glass. Describe how many different products comprise several different materials and state that these materials have to be separated in order to enable recycling. One of the things we're going to get into is composite materials. Now, these are engineered materials that are made up of multiple different components. Most of the time to recycle these, you have to break them down to recycle them. For example, reinforced concrete, or concrete that has rebar in it. Concrete can be broken down and recycled. Metal can be melted down and recycled, but you have to separate those things. Reinforced concrete is actually fairly easy when you compare it to something like fiberglass. Fiberglass is a composite material that's made of a textile fiber, and it's also made of a ceramic or polymer shell. Those individually can be recycled, but when they're combined together to form a composite, it's usually very difficult to recycle those things, if it's even possible. Discuss the issues underpinning the economic recycling of materials. You need to consider collection, energy and processing considerations, and then redistribution. In order to recycle, you need to collect, sort, and clean them. Now, at St. Ed's now, we have these single stream recycling containers, so it's a lot easier. There's actual technology now that can automate this whole separation process. It makes it a lot more efficient. Recycling uses energy just like all other refining processes. Like I said, some materials require a large amount of energy and chemicals, like paper, or for paper to recycle. And then the recycled product needs to have the same or similar quality characteristics as the original, or manufacturers might opt for unrecycled materials. That is, if you can recycle something but it has a very low quality, no one's going to want to use it. Design for disassembly is another thing that actually involves making a product so that it can be easily disassembled and separated so that parts can be either reused or recycled. On building construction, this is known as deconstruction, where you actually carefully take apart a building rather than just bulldozing the whole thing. The Habitat for Humanity Restore is a neat place that we've talked about before that actually takes a lot of these components that were moved from houses and then resells them for use in new homes. Explain that design for disassembly is one aspect of design for materials and will facilitate recycling products on disposal. Now remember, to recycle, products need to be cleaned and broken down, and so the actual materials can be recycled. Making them so that they can be easily and quickly disassembled makes the recycling process much faster and much more efficient. It's usually a bad idea for recycling if you use adhesives that can't be broken down, like thermoset adhesives. Those are not very recyclable, or fasteners that have to be removed. And finally, discuss 2 strategies that designers could use to employ design for disassembly. Now, use components that are made from a single material rather than composites. That makes those individual components easy to take apart and disassemble. Use thermoplastic adhesives. Thermoplastics, unlike thermosets, will actually break down when heated. So a thermoplastic will come apart when you heat it up. It's pretty easy to do. And then use snap fittings and types of parts that are made in to the aspects of the product instead of welding and gluing. And then there's a link to an article that you can read on more information about design for disassembly.